Hello professors and other viewers. I'm recording this video to showcase the feasibility of my proposed approach along with making a quick demonstration of how evolutionary algorithms and generative designs work with finite element method in an architectural design environment. In this video, I will show you an example of finite element model optimization through evolutionary algorithms on a tall building that is built from hexagonal steel frames. To make this project, we are using grasshopper settings of the Rhinoceros 7, and in grasshopper we are using Launchbox and Kiwi 3D plugins in order to create our mesh and make finite element analysis along with grasshopper's already given traits. I will make quick explanations of each step of the analysis and each step of the code, but I will provide an additional document in Microsoft Word format that further explains, in more detail explains each step of the analysis. The first 5 steps of the code is actually about creating a mesh and dividing it into hexagons that is constructed out of steel frames and providing a display in the Rhinoceros. So as you know, we can actually do all of this analysis without providing any visual display. However, as stated in the research proposal, this won't actually will be beneficial for the non-analysis experts. For a non-expert to get the grasp of the analysis outputs, the displays are actually very beneficial. So we are providing a slide display. Providing displays in great detail will slow down the model, therefore will be unbeneficial for the analysis itself. So as you can see, in first 5 steps we use basic commands of the grasshopper. We are creating a polygon, rotating it to make it align with x and y axes. We are extruding it by 100 meters to create a tall building like model. And let me disclaim this. This obviously, as you can see, is not a detailed structural analysis. It's even as analysis that cannot be applicated to real life in this state. However, it's doing its work by proving us that we can use and we can combine evolutionary algorithms with finite element methods to actually make statements in structural design phases of an architectural design project. And as you can see, in step 4 we are creating surfaces for the grid tool to, in further steps, divide them into hexagons. And this is actually our first step of creating our model. In step 6, step 7 and step 8 we are defining the properties of steel beams. On the left side of the screen you can see that we actually define each of these lines in hexagons as steel beams. So we are providing the program that beam length, the beam weight, and the weight of the structure, which can be thought as the sum of all beams weight. After defining the properties of steel beams, we can actually create a gene pool for our evolutionary algorithms that we will use in Galapagos plugin. So what is a gene pool? The gene pool is actually like an ID card, identification card of our each design. So as you can see, in this gene pool we are providing the numbers for how many times this object, each wall of the structure will be divided in horizontal and vertical directions. And we are setting these parameters in a gene pool. When we get to this side, this is the thickness and the diameter of the beam, and we are adding this to gene pool 2. So that means our designs will be defined by the horizontal and vertical numbers of hexagons in a wall of the building, and these beams diameter and mid thickness. After creating our gene pool and defining our beams, we can start with the steps of finite element analysis by converting our beams to finite elements, which are line frame elements in this case. As you can see, now we are giving the inputs that are necessary for finite element analysis, like beam outer and inner diameters, the locations of diagram beams, the material for steel beams, and we are summing all of the beams information in this command. In steps 9.2 and 9.3, we are adding a surface load to get the informations and get a fitness number out of it, which I will explain later. And of course, in finite element analysis, we have to define supports and their conditions, as you can see in support command. In step 10, we are defining the finite element analysis conditions, like we are carrying out a linear analysis, we are using this model, and we are looking for displacements in x direction related to the surface load we have given in step 9.3. And the last step we have to take before creating or starting a evolutionary analysis, we have to define a fitness count for the algorithm. So what's a fitness count? The fitness count is a imaginary number that the algorithm will look for and either have to maximize it or minimize it at our command. So in this analysis, we want to minimize the structural weight and we have to minimize the displacement. However, minimizing the structural weight at a degree will increase the displacement. So this is a key point in optimization, multi-objective optimization. If none of the parameters inhibits each other, the result will be 0 or infinite. Let me give an example. If I say to one person to buy me the most amount of apples with spending the least amount of money, if I don't give any inhibitors or any constraints, the person will either buy infinite amount of apples or 0 amount of apples, because one of the scenarios will give me the most apple, while one of it will give me the most amount of money. So we actually have to select our parameters in multi-objective optimization in a way that some of them will inhibit each other to actually get a accurate result. So as you can see, at the end of the code, we have a text display section that will show us the results, which will show the genome of the design, its cost, its weight, and its displacement. Now I will run the analysis, but I will stop the video before running the analysis because it actually takes a quite amount of time. So before starting the analysis, let's check our identification card of our default design, which is seen here. So as we've seen from the ID card, our design has divided by 25 pieces in vertical direction and 19 times in horizontal direction. We have a beam diameter of 24 centimeters while having a beam thickness of 2.5 centimeters. So let's start the design and let's start the algorithm and see if our design is optimal or not. so the analysis had been completed, but because of my computer being a very low-end performance computer, it is actually very slow to demonstrate the results from the grasshopper itself. So I've prepared a table in Microsoft Word, and I will present the results to you from here. So first, in Galapagos, we have a few options to configure before starting the analysis. So you can increase the maximum stagnant and population or initial boost to make a more precise analysis, but the problem we are solving here is actually a very easy problem for evolutionary algorithm to solve, and it takes so less time. So we actually can keep the maximum stagnant and population at 10. And we can see how easy it is for evolutionary algorithm to solve that, because as we explained before, the best score and worst scores means the best and worst fitness score that is coming out of the analysis, and we can see that our final result at the 6th generation is 35, and even at the zeroth generation we can see that we are already at the fitness score of 37. So we see that even though the worst score is getting better, so that means the worst score means that the worst design in a generation, and the best score means the best design in a generation. So we can see that even though the best score is not getting any lower, we can see that worst score in each generation is decreasing. So that means algorithm cannot make a design that surpasses the previous generation's best, but it's producing better and better results. So the threshold of worst design is also decreasing as a matter of fitness score. When we get to the second generation, after the sixth generation, after the sixth generation, when we look at the analysis, we can see that in this line, the iterations doesn't make any improvement of further generations. So that means that the best design of the predecessor is not any better from its ancestors. So at that rate, we manually, or the algorithm automatically stops iterations to prevent unnecessary data. So as we can see, the best fitness score we are getting from multiplying the deformation in x direction and the weight of the structure is 35. And the ID we are getting from the genome is 10, 15, 19, and 2.5. So that means the best design in this gem pool is dividing the structure horizontally 10 times, 15 times vertically, having 19 centimeters having 19 centimeters diameter of steel beams, and giving them a mid thickness of 2.5 centimeters. And in here, figure 9, we can see the optimum design output for the according to the algorithm, and we can see the deformations, as you can see at the figure 9b. So this was the results of my demo in the terms of combining the finite element model and evolution algorithm. Thank you for listening. Have a good day.